Okay, let's talk about esters. Esters are really cool. Again, I wish that I could do that really sweet lab with you. But since the primary sense that you need to engage in order to know if you did the lab right is our sense of smell, it's really not useful. But something about esters. Oftentimes, when you check packages, and they might say something like, natural and artificial flavors. Many, many, many times when you see those words, there are esters inside of your food. And this is good. Oh, like, just because they are quote unquote chemicals doesn't mean they're bad. As a matter of fact, they're good. Um, like, I don't understand. Well, I do understand why people have this fear of the word chemical because it comes with a connotation for a lot of folks of something made in the lab. Oh, we don't know what it does, etc. And oftentimes, yeah, there are some chemicals that we don't know that they end up being harmful. I mean, look at what we learned about DDT and polychlorinated biphenyls, PCBs, all of those the dirty dozen, those nasty chemicals, and we made them to do a job, and then we realized, oh crap, these are like really bad for the environment, and they bioaccumulate, and they biomagnify, and they harm all kinds of organisms, and they also completely affect human health in very deleterious ways. Esters, on the other hand, these guys are nice. They smell like good stuff. So if you go and, for example, you get some grape Kool-Aid, um, the chemical the chemical ethyl anthranilate. Uh, that's grape flavor. So a lot of these flavorings are, again, esters. And they are formed by a nice little reaction, and the reaction tells you what it does, thankfully. It is called an esterification reaction. In other words, a reaction that makes an ester. What is the general form? In other words, like what does the molecule look like? Well, I'm going to put a little wild card down here. I've got a carbon double bonded to an oxygen, a carbon single bonded to an oxygen, and then a different wildcardy type group. So this might look a little bit like your carboxylic acid. And if that's what you kind of see in here, give yourself a pat on the back. This is actually made out of two kinds of molecule that we already covered. So that's sweet. Like, they are made out of an alcohol and a carboxylic acid. And usually you need to add something to help it go. Usually we use sulfuric acid as kind of what we call a catalyst. It helps the reaction go, but it doesn't get added to any of the part of the molecule. It just kind of, it makes it easier for the reaction to go. Just like how an enzyme in a human body or in a living system helps chemical reactions happen, we can use just normal chemical catalysts here. And so we get our nice, ester. So I'm going to show you how to do an esterification reaction. And I'm going to do it in the easiest and most effective way that I know how, because it would be stupid to do it any other way. So I'm going to be drawing these molecules a little bit weird, but bear with me. So whenever I draw alcohols and carboxylic acids by themselves, I put the OH on the right-hand side if I can help it, and I put the C double bond OOH, the carboxyl group, on the right-hand side. So what I'm going to do is I'm going to write down an alcohol. Oops, didn't mean to put a comma there. I'm going to write down an alcohol, I'm going to write down a carboxylic acid, and we're going to talk about how the reaction happens. So let's use words first. So we're going to use our simplest alcohol, methanol. And let's use ethanoic acid. The way that the words work is, let me change colors here. We're going to be keeping parts of the word that are the most important. So the first part of the word, and the reason why I put the alcohol first is because the first part of our new chemical name comes from the alcohol. So we take the meth prefix and we call it methyl. Kind of like how we saw that a branch with one carbon is a methyl group. Simple. Then we take the second word, and we're going to get our second word is going to be generated from comes from the carboxylic acid. And it is going to be ethano. And then instead of ick, it gets the ending sound 8. So this molecule is called methyl ethanoate. There's one last thing that gets made here, and we'll see that it's abundantly clear when we actually do the esterification reaction, and that's we make a molecule of water. Okay, so let's take a look. I'm going to draw my methanol molecule. And I'm going to make sure that my OH is pointing towards the right. Now, here's where it's going to get weird. I'm going to draw my ethanoic acid molecule, but I'm going to make sure that the C double bond OH is pointing to the left. It's going to be pointing towards the OH of the methanol. The reason why is because it makes your life so much easier. So ethanoic acid is 2 carbons, 1, 2, a C double bonded to an O, and single bond to an OH. And then I'll draw the carbon or the hydrogens. It's not a big molecule, not a lot to do. There we go. So the reason why I'm pointing it towards the OH of the alcohol is because this is where the chemical reaction takes place. So what's going to happen? You need to really pay attention to this because It's easy to get lost. So I've got my molecule of methanol with the OH pointing towards the business end of the ethanoic acid, and vice versa. My ethanoic acid business end, the carboxyl group, pointing towards the OH. Here's what we're going to do, and I'll show you what's called the intermediate, the middle step. What's going to happen, and just so you know, it is more complicated than this in real life, but in Science 30, you don't have to really get into all the complicated stuff. Here you can see an OH group, and you can see a hydrogen. Now, if you count those up, just take a moment. We have 2 hydrogens and 1 oxygen. Huh. That's going to be our H2O. So usually what I do is I just make like a little side arrow and I say, okay, this forms an H2O. Now we have to consider, okay, what's left? What else is still here? Because the H2O has been taken care of. What's the methyl ethanoate going to look like? Okay, so I'm going to draw everything that's left. And then we're just going to use our brains, because that's how this works. So here's my C, here's my O. Remember, the H that used to be there is long gone. It is now part of a water molecule, so it's enjoying its life as a water molecule. There's my other carbon. There's the C double bond to the O. And if you look at this, something's going on. This oxygen should have a bonding capacity of 2. But if you look at it, it's only got one thing attached to it. So it's missing a bond. Likewise, you look at this carbon. It should have a bonding capacity of 4. But it's only got 3 lines coming out of it. So that means that you have 2 things, 2 atoms that require a bond. That's kind of interesting, isn't it? Well, you know what? We're going to give the people what they want. We're going to give those 2 atoms exactly what they want. We're going to give them a bond. And we're just going to draw that bond like that. We'll clean everything up in a sec. But I'm just drawing that to show you that there is a bond that forms between this carbon and this oxygen. So let's clean this guy up. There's my C. There's my hydrogens from that used to be part of the methanol. There's my oxygen. We're going to draw the oxygen to the carbon bond in blue to show that that was that new bond that was formed. There's my C double bond O. That used to be, that's right here. And then my carbon with the hydrogens. So there you have it. There is a molecule of methyl ethanoate. How do we identify each part? Well, the carbon that has the double bond, that's my ethanoate portion. And the carbon that has only a single bonded oxygen, that's my methyl group. Hey, look, it's a CH3. That's literally what a methyl is. So we'll do a couple more examples because esterification reactions really burn people, in particular on things like the phenol, which obviously we're not going to have, but Still, we do assessments, so let's do a couple more. So let's do propanol, and let's make sure that it is propan 1 all. In other words, the alcohol is going to be on the end carbon, not on the middle carbon. And let's mix that up with, I don't know, let's do butanoic acid. So we'll draw our molecules. The sweet thing is, once you understand how the naming works, the first word comes from the alcohol, the second part comes from the carboxylic. The sweet thing is, you can use that to help you determine the name. And then from there, you can even help use that to determine the structure. So this will be propyl. And butanoic acid will turn into butanoate. So let's draw these molecules and let's do an esterification reaction. So 3 carbons, 1, 2, 3. My OH is on carbon number 1, but we're facing it. We always want to face the important parts of the molecule towards each other because that's where the reaction happens. And then butanoic acid, okay, so C, double bond O, O, H. And then so since it's butanoic, we need 4 carbons total. There we go. And there's our molecule, propan 1 all, and butanoic acid. We got everything lined up the right way. We snag our OH from the carboxylic acid. We snag our H from the alcohol. That makes an H2O. Now we just redraw everything without the H2O part that we just removed. So 1, 2, 3. And there's my hydrogens, got to have those. And now there's my oxygen from here. And now here's my C double bond O. And then the rest of my carbons. Boom, boom, boom. Oops. There we go. Now we look at the molecule and we say, okay, what's missing? This guy only has 1 bond. This guy has 3 bonds. It needs 4. So we form a bond between. And then we simply redraw the molecule looking all nice. And remember, we have to include in our when we write it out 1 molecule of water. So let's redraw our molecule real quick. And then throw the little tickies on there for hydrogens. So there we go. That's propyl butanoate. And whenever there is this feature here, we call that an ester link because it links my carboxylic acid to my alcohol piece. One last thing, let's say we have to go backwards. Let's say we're given a structure and we have to explain what the name of it is. Okay. So, and I'm gonna do it in a way that is a little bit more difficult or, pardon me, confusing. And then I'll put out all of the hydrogens as tickies. Okay. So you look at this and they say, okay, what is the formula for this molecule? Or sorry, what is the name of this molecule? So the way that I would do this is when you have a lot of practice and you've been doing this and you've been doing organic chemistry for years, you just get a sense of it. And some students, you're gonna look at one example and be like, oh, I completely know how this works. Some of you won't, and that's okay. So when I look here, I am looking for the carbon that does not have a double bond to an oxygen. So this is the carbon chain that does not have the double bond to the oxygen. It's only got a single bond. So now I'm going to write down the name of this part of the molecule. And so it's meth-eth-prop. So that's propyl. Then I'm going to look at the other part of the molecule. How many carbons does it have? It's got 2. So that means that this part of the name, actually I won't draw an arrow, and the reason why is going to be obvious in a sec. The second part of the name is going to be ethanoate. So what if you're asked to go backwards even harder, and what if you're asked to draw or select from a list what the original ingredients were, the reactants to make this guy? Okay, if you can identify the 2 parts of it, you're golden, because now I can say, okay, propyl must have come from propanol, and ethanoate must have come from ethanoic acid. Then it's just a matter of drawing them. Okay, so propanol, it's going to be propan 1-ol because my bond is on the end carbon. So that'll be 1, 2, 3, and my OH on the end. And my ethanoic acid is 2 carbons, carboxyl group, and there's my ethanoic acid. So you take propan 1-ol, you take ethanoic acid, you put them in the same beaker or the same flask, you heat them up to around 70 degrees Celsius, and you hit them with a drop or 2 of sulfuric acid, and that's going to get the reaction going. I'm just going to let you know what this particular chemical smells like. So this chemical, propyl ethanoate, has the odor and flavor of pear. And so esters, these molecules, they get put into food, artificially flavored food. But if you ground up a pear, you could find this molecule. So this molecule is quite literally made by the living processes of the pear, the fruit, to taste good. And the whole idea of fruit is to trick animals into eating them. The seeds of the fruit can't be digested. So if you're like a moose or a deer or some kind of animal that eats fruit sometimes, you go up to a pear tree. Maybe there's some pears that have fallen on the ground because they've fallen off the tree because they've ripened fully. You eat up that pear, and why do you eat it up? Because it tastes good, because of this guy and sugar, and obviously many other molecules, but primarily sugar and this guy, this propylethanoate. And then that means you're also eating the seeds because animals don't pick out the seeds or anything like that. They don't care. They're not babies like human beings. So then you digest that pear, seeds and all. You don't break down the seeds. They stay, they have a protective coating on the outside that makes it so they don't get digested by the animal. And then maybe a day later, or however long it takes for food to pass through a deer's digestive system, because I have no idea, the deer has to go to the bathroom, and they also don't go in toilets. They just kind of go on the ground. Now you got a pear seed on the ground. Not only is it on the ground, it's surrounded by poop. It's surrounded by fertilizer. Plants are smart. Like they get animals to do a lot of their heavy lifting for them. And the most amazing one, well, pollination by bees and bats and butterflies, that's cool. But I personally think that inventing fruit that tastes good to trick other animals is like, I don't know, it's beautiful. It's nature doing a really cool thing. One last one that I'm gonna leave you with, not another ester, but just one of these guys. I can't draw. The avocado. Let me see if I have a paint bucket. Paint bucket mode. Lightish. Is it going to do the color? It's not working. I'm going to have to scribble. Anyways. Interesting thing about avocados. Avocados are a fruit. This is true. However, have you seen the size of an avocado pit? They're pretty big. You might wonder, based on what I just told you about fruit being a way to trick animals, what animal ate avocados and pooped out the seeds? Well, they don't exist anymore. There was a giant sloth that lived thousands and thousands of years ago. And they were the only animal that lived in the area in Central America where avocados grow or are endemic, where they are from. Their original place, their origin. And these giant sloths, like I said, were the only animal big enough, with a big enough digestive system to carry and distribute, poop out, the seeds of the avocado. The only reason why we still have avocados today is because indigenous peoples in that area started growing avocados on purpose, farming the avocado tree, planting them on purpose. So if it weren't for the giant sloth, we would not have avocados at all. They would have gone extinct. If their only way of getting around and getting the seed from A to B went extinct, then they would have no way of getting their seeds around, and they would very rapidly die out. But since indigenous people in that ancient time figured out we can take seeds and we can plant them, that's why we have avocados. And what probably happened initially, they probably didn't plant them on purpose. They probably ate the avocado fruit, the outside, the part that, modern humans really like too, and they probably just threw the seeds on the ground. And as soon as they realized, because ancient people, believe it or not, had the same brains as us. They might not have had school and education in the same way, but ancient people still had, brains that are fundamentally identical to modern humans. As soon as they saw, hey, hold up, the place where we throw all of our avocado, those hard things that are impossible to eat, we throw them all in a pile and then we get an avocado tree out of that. Hold on. Why don't we put these in a special place and they'll grow into avocado trees? So they did that. And I mean, human beings are really smart. We figure stuff out. So, esters, a recap. They're molecules that taste good and smell good. We put them in foods. Fruits and vegetables make them naturally. We also make them in labs. And they are put into foods and perfumes. And they are made using an esterification reaction where the OH from the acid, the H from the alcohol, they hook up and they make a water molecule, and then a chemical bond between the oxygen and the carbon is formed, making an ester link. And then we have an ester. Alright guys, next video is going to be on polymers. See you soon.